Hello everyone, I'm Shih-Yu. Today I am presenting our paper, DrivingVibe, Enhancing VR Driving Experience Using Inertia-based Vibrotactile Feedback Around the Head. This is a joint project with my advisor, Professor Neng-Hao in National Taiwan University of Science and Technology and Professor Mike Chen in National Taiwan University. I'd like to show my thanks to my lab mate and the partner who joins in this project across different universities. In summary, we developed a head vibration system and designed two types of vibration patterns for VR driving to enhance the overall experience. Most VR contents could provide visual and audio feedback, but in some situations such as VR racing games, still left users unsatisfied. One of the reasons is lack of appropriate haptic feedback. We aim to enhance the immersion and realism in VR driving scenarios through motion experience and tactile sensation. We believe the head is a viable entry point for this enhancement, as it houses many receptors for dynamic sensations. Additionally, modern VR devices require wearing headset, and the latest VR headset also introduced vibration feedback inside as one of its features. Therefore, we decided to experiment with designing feedback on the head. In summary, our objective is to create head vibration feedback for enhancing VR driving experience. The related work can be broadly categorized into motion simulation technique and providing vibration feedback on the head. We will talk about some works that inspire us later. Head blaster utilizes air nozzle to apply thrust to the head, simulating inertia. This highlights the significance of inertia force in enhancing related experience. The motion platform provides realistic feedback through the movement of the entire seat, essentially mimicking inertia sensation in principle, but it still requires large space and complex machinery. Motoring employs vibration motors surrounding the head to generate the tactile motion and develop relative perception models. We adapt a similar hardware design and will assess the potential of applying tactile motion to driving experience. Haptic head displays vibration motors on the head. Utilize multiple motors vibration to provide directional cues in three-dimensional space. We will also draw inspiration from this concept to stimulate different directions of inertia. Walking by uses head vibration feedback to reduce motion sickness in VR walking experience. According to this paper, we knew that vibration around the head might stimulate the inner ears, and we will attempt to apply this to the motion experience of driving as well. Next, let's move on to our system implementation. We went through 3 hardware iterations for our devices. The final version of the devices incorporates several enhancements. In conclusion, this system can be comfortably worn on the head and it operates without the need for wired connection to a computer. In order to connect to our device to the state-of-the-art VR games, we use Motion Telemetry API, which is an interface that allows developers to access and gather data related to the motion and the movement from the games. Next, come to the most crucial aspect, our feedback design. Our first design is the 3D inertia-based approach. In this pattern, our focus lies on designing the directionality of the vibration feedback. Our objective is to induce sensory motor contingency through the directionality of vibrations, creating a connection between the sensation of feedback and real-life experience. This enhances the effectiveness of feedback by linking it to tangible experience. First, we needed to determine the timing for providing feedback. To achieve this, we identified crucial driving experience and designed feedback for each. In the final version, instances for feedback including turning, acceleration, deceleration, vehicle movement on rough surface, and cold start. The process of acceleration from the stationary position. Next, we will proceed to discuss the design for each of these events. First is the directional cue. As you can see, this approach involves providing feedback to the corresponding area of the headband based on the directional of inertia force. In this example, during a right turn, the inertia force is directed to the left, resulting in vibration on the left side of the headband. We read the real-time inertia force value and directions from the games and trigger vibration on the motors in proximity to that direction. Next is the pattern from simulating vehicle body movement, utilizing tire movement to create a sense of undulation in different corners. In order to replicate the sensation of different road surface, we studied various in-game physics parameters. We realized that tires being in direct contact with the ground exhibit different behavior based on the surface material. We can use the rate of suspension height change to infer the current road surface material. Lastly, we have the co-star design. We provide tactile motion feedback that brushes back forward on the both sides when the vehicle starts. Apparent tactile motion is creating an illusion of single movement point. This feedback often feels like flowing sensation or something brushing against the body. We aim to utilize the phenomenon to enhance the driving experience. As the sensation of high-speed driving closely resembles tactile motion, we initially apply it during movements like acceleration, high speed, or high engine RPM. However, we found that tactile motion is more artificial form of tactile feedback. Therefore, we conclude that tactile motion should be applied at specific moments, such as the start of the race or the use of acceleration items. Finally, we decided to incorporate tactile motion during the vehicle's cold start. This is because during the start, strong feedback is expected, but the inertia force are not high, and the cues from the previous pattern might not be as strong. Tactile motion can complement this by adding to the overall feedback experience. Since the 3D inertia-based approach relies on the in-game motion data, which is either provided by the game developers or obtained through telemetry APIs, we found that most driving games already have some form of controller-based haptic feedback that vibrates at similar key events as those mentioned earlier. Thus, we developed the mirroring approach, which leveraging existing controller-based haptic feedback to provide the same feedback to the headband. By observing the intensity signal from the controller motors, you can see that the controller vibration happens at the selected key events as well. The main difference between two approaches is the intensity. We attempt to replicate this vibration information onto the headband. Initially, the intuitive approach was to map the left motor to the left side of the head and the right motor to the right side. However, we discovered that this arrangement results in poor performance. The directional distinction of left and right caused confusion. Additionally, when a controller vibrates, we typically don't distinctly feel which motor is active. It's more like unified vibration across the entire controller. Due to this reason, we decided to average the intensity of two motors on the controller and apply this average value to each motor on the headband. This approach made the headband's role similar to that of controller. Whenever the controller vibrates, the entire headband will vibrate synchronously. Compared to two designs side by side, we can observe that feedback during acceleration is more contextually aligned. The most significant distinction is that mirroring lacks directionality. Moving forward, let's discuss the final evaluation. Our objective was to demonstrate that both designs significantly enhance the experience. By comparing two designs, we can also discern the difference in outcome due to the presence or absence of directionality. Therefore, we established a baseline comparison without headband vibration. Adding our two designs, we had a total of 3 conditions. In the experience, there were 4 types of experience divided into active and passive scenarios. There were 14 male and 10 female participants, all of whom scored below 70 on the motion sickness susceptibility questionnaire. We collect data on immersion, realism, enjoyment, and comfort for each experience and condition. After completing all 3 feedback modes for a specific experience, participants were required to rank their experience based on the immersion, realism, enjoyment, and overall performance. This ranking process was conducted again at the end of experience to understand preferences across different contexts. In the final result, we observed that both designs exhibit significant difference from baseline in terms of immersion, realism, and enjoyment, while comfort rating remained within a moderate range. In the rankings, the two designs collectively accounted for nearly 19% of preferences. Notably, over half of the participants favored 3D inertia-based design. In a summary of the results, studies show that DrivingVibe could enhance the VR driving experience, and 3D inertia-based design could have higher preferred and improvement in the experience than mirroring design. Lastly is discussion and conclusion. In our two approaches, they could complementary nature another one. The mirroring approach supports more games with lower feedback fidelity, while 3D inertia-based design provides higher feedback fidelity for games with telemetry data. In the future work, we can explore further detail in apparent tactile motion feedback designed to enhance its interpretability and also use the nonlinear intensity to improve pattern precision. Other potential applications could involve implementing similar systems for feedback on other motion experiences like flying simulator or different body parts. In conclusion, DrivingVibe introduced two head-based vibration feedback design aimed to enhancing dynamic experience in VR. Our study demonstrates significant improvements in immersion, realism, and enjoyment, with 88% of participants favoring our designs. Furthermore, our comparative analysis suggests that understanding the directional cue of vibration can further enhance overall sensation. This is the end of my talk. Thanks for listening, and if you have further questions, please contact me via my personal email and I am happy to answer any kinds of questions.